3 minutes in. Everybody else okay? You guys okay? I'm in the double digits of students. I'm so happy. The big 10. Base 10. Okay. So if there's no questions, which I'm a little surprised about, but that's okay. We'll get back into what we left off with last time. We'll finish up chapter 13, and then maybe we'll take a sneak peek at the practice final, right? All right. Do this first, Jeff. There you go, buddy. Bum, 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 bum. Oh, I see. That's not me. I need me there. I lost. There we go. Oh, she's back. Okay. Now. Oh, look, it's us again. All right. So the last thing we left off talking about was sequence notation, right? So if I give you a sequence like this, what you got, Jeff? It doesn't really matter. N minus 2n squared. I like it. Right? So it's just like function notation. A1 would be 1 minus 2, and so forth. If I wanted A111, you would just put a 111 in there to figure out what that component of the sequence is. All right, so it's just kind of an alternate way to function notation, but specific to sequences. But it works the same way. All right, that's kind of boring. What's a little more interesting is if I give you a sequence. Let's see, Jeff, can you do it, buddy? Let's find out. Yeah, let's see. That'll be nice. So it could have been mean and actually have those reduced. I'll be even nicer. Here we go. Can you guys come up with a definition for the sequence elements? So what are the obvious patterns? The bottom is going to be the easy one, right? What? This is A1. You with me? So N is 1 here. A2, A3, so forth. So what's the bottom going to be? If I want the first one, it's 2. If I want the second one, it's 3. If I want the nth one, what's here?
N plus 1.
N plus 1. Is everybody with me? All right. Top is slightly more interesting, but actually not interesting at all.
2n.
2 what?
2n?
No.
Nope.
Because 2 times 3 is not 8, right?
Is it 2 to the n?
2 to the n. I like it.
Oh.
I like it. So that is an interesting, especially if I would have given it to you reduced. That would have been a little more tricky, right? Okay, let's see, what else we got? Oh, let's do this. Kind of an interesting little side note with sequence stuff is the idea of a factorial. Does anyone who's with me right now know what a factorial is? Anybody ever heard of a factorial before? Anybody? Has anybody noticed all the punctuation that's on your calculator? Does anyone know what I mean when I say that? If you have a TI calculator, do you see a comma above the number 7? There's a comma above the number 7. There's also, if you hit, I think you have to hit math to see this. And you go over to number. Well, shit, where the hell are you? I forget where. Oh, yeah, it's in probability. There is an exclamation point. So a factorial is an exclamation point. That is just a choice that was made to represent the idea of a process. Sort of like we had to come up with the square root symbol to mean what it does, right? So for some reason, they're all sitting around the corner. What are we going to call this damn thing? What are we going to call it? You're so excited. Let's call it a freaking exclamation point. Okay. So this is not n. This is n factorial, and it means this. Get out. 1. All the way down to 1. Become a 1. Ah. So for example, 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1. And you know, whatever the hell that is. What is that? 120, 720. Is that 5,040? I don't know. I lost track of it. I feel like I should know. I think that's what it is.
It's 50/40.
Ah, sweet. Oh, Jeff. So if I saw this, what you got, Jeff? Sure, you can do 3 to the n over n factorial. Then you can kind of make this. If n is 1, it's 3. Oh, quick thing about, well, I'll do that next. This will be 3 over 1. And then 2, it would be 9 over 2 factorial is 2 times 1. And then 27 over 3 factorial is 3 times 2 times 1 is 6. And then you can reduce that, so forth. Okay. Factorials are very useful for probability problems. There's a very basic probability problem, like how many license plates can you make using only letters, not repeating any letters. So it'd be like 26 options for the first thing, and then 25 options for the next thing, and then 24 options for the next thing. So somehow that would be, so let me see if you guys are kind of with me. Let's build this up. So if I have a license plate, it's got 7 spots. And let's just make it simple. We'll say we're only going to use letters and no repeats of a letter. How many 7 letters can you put together? How many things can you put together like that? So there would be 26 options for this, 25 options for that, all the way down. So it would be, now watch what this would be, 24, 23, 22, 21, 20. So it's 26 factorial divided by 19 factorial. Let's see what that's true, because this would be 26 times 25 times 24 times 23 times 22 times 21 times 20 times 19 times 18 all the way down to 1. So isn't that 19 factorial right there? Wouldn't that just cancel? So what I'm saying is, if you get tired, so if you had to do 350 factorial, isn't that 350 times 349 times 348 factorial? I'm tired. Wouldn't that mean keep going? So if you had 350 factorial divided by 348 factorial, you could do this, these cancel, and the answer is just that times that. All right. Okay, so that's what a factorial is. And one of the first places it was used was in probability theory. But you see it all the damn time in mathematics, also pure mathematics, not probability theory. So you're going to see that in some of these sequences. Oh, what the hell is this? What do you think that would be? Why does this seem to not be able to work with this idea? The
Does it have
definition
to be
of
larger than 1?
it seems like it should be, right?
Mhm.
N factorial is n times n minus 1 all the way down to 1. So it seems a couple of things. It seems like this could not be anything but a natural number, meaning it couldn't be negative, and it couldn't be 0, and it couldn't be fraction, right? All of what I just said is incorrect. But for us right now, that is primarily what it is. But now watch why this is okay. Let me see if I can remember this. This is out of nowhere for me. I forgot to even remember to look this up. 3 factorial is 4 factorial divided by 4, right? I mean, can you guys, is that okay? What's 4 factorial?
4 times 3 times 2.
And what's 4 factorial divided by 4? It's 3 factorial. Is that cool? So 2 factorial is 3 factorial divided by 3. You guys still with me? 1 factorial is 2 factorial divided by 2, and 0 factorial is 1 factorial divided by 1. This is not the only, this is not even really a proof, to be honest, but this is not the only way to show that 0 factorial is 1. All right. There's another kind of way to talk about this. Real quick, I don't want to leave this because I kind of love the whole probability thing with this. If I had 4 people, how many ways could I rearrange them? Right, so I'm going to stand them up against the wall and I want to just arrange them in every possible way. Well, how many people could I put here? 4. Everybody semi with me? Well, once I pick somebody to put there, how many people can I put here now?
3.
3. So this is obviously 4 factorial, right? If I had nobody, if there was nobody there, not even me, how many ways could we arrange them? One way. There's one way to it. I don't know if you guys get that either. This isn't, I don't like to start with this one because it's a little bit conceptual, but that's another reason why this is 1, because it sort of represents the number of ways you can arrange something. Well, if I don't have any money, how many ways can I arrange all my money on the table? One way, there we go. I'm done before I started. I like that, to be honest, but that's not really mathematical completely. Yeah. Okay. Enough of factorial. Factorials are really weird little dudes. You're not used to symbols being punctuation, and you don't immediately see the usefulness of it when you first encounter them. But once you see them, if you go further in math, they're every damn where. Okay. Let me come back to where I was. Where was that, Jeff? Oh, yes. Okay. Let's talk about recursive sequence formulas. So recursive sequences, I could say. One that we've already seen is this one. What are you doing, Jeff? I wish I knew. Then I could really help. Okay. Right, we talked about Fibonacci sequence last time. If I ask you to create this for this sequence, can you come up with a definition, some kind of formula way to write this so that I can get all the terms of this? That would be really evil for me to do because it's not really possible. So what you have to do is, with a lot of recursive sequences, you have to have what are called seeds. So I have to know that A1 is 1 and A2 is 1. And then what would I define A3 to be? A1 plus A2, correct? And then what would A4 be?
A2 plus A3.
Crazy. So what's AN? Let's see if you guys get this. If n is 3, this is 1, and this is 2. If n is 4, this subscript is 2, and this subscript is 3. You can do it. You don't think you're allowed to, but you can do it. This would be A sub what? You could do it.
N minus 2,
Kick ass.
and then n minus 1.
Yes, there you go. This is a recursive formula. Recursion means it's based on itself. The next sequence element is based on one or several other previous elements. So this is a recursive sequence definition. So let's do one that's a little less freaky. This guy, people have studied this their whole life. And there's a lot, anyway, there's so much to the story. There's something that I discovered about 7 years ago that I every now and again come back to that's like taking this to other dimensions. But I'm not going to do that tonight. Let's not do that. All right. Come back down, Jeff. Come back down. It's all right. That's some weird shit. Now I'm going to have to do that. All right. I got to get it out of my head. Stop it. All right. So what if I had a definition like this? AN equals, you can do it, buddy. 2n plus AN minus 1. How many seeds do I need? Such a weird question. You didn't think I would ask you ever in this class. How many seeds do I need? I need 1 seed. I need to know what A1 is to get this started, right? So if I say A1 is 7, can you come up with the next 3? What's A2? What's A3? What's A4? So you can be very formulaic about this, especially when you're brand new to this. So what is officially A2 by this definition? 2 times 2 plus A sub 2 minus 1. And of course, A sub 1 is 7. So there's not a damn thing wrong with being very explicit with your work when you're first learning this stuff. So then you would write A3 equals 2 times 3 plus A sub 2, and then you throw that shit in. So it becomes a lot more like function notation. You kind of, even with recursive formulas. So A3 would be 2 times 3 plus A sub 2. And of course, A2 is 11. So the next sequence element always references the one before it for this example. And what's A4 going to be?
$25.
25, 11. 2 times 4 plus the last thing, so 8 plus 17, 25. Kick ass. So sequence notation, sequence formulas, again, I've said this a couple times already with some things, but compared to some of the stuff we've done, you can just eat this up, right? And the less comfortable you feel, the more you can show yourself from the definition of the sequence. You just fill it in. You don't try to do too much in your head. All right, I like it. Okay, I'm trying to remember. I think that's everything from that section.
Can we do one more of those?
Sure. Let's do one with a couple of seeds. Let me kind of define this one a different way. That looks funky, Jeff. So let's say that I know A1 is 2 and A2 is 3. And by the way, real quick. I don't know if you're gonna, I think it's kind of obvious I need 2 seeds. But if I try to use the formula to get A1, what would N have to be? If I want this to be A1, what would N have to be?
0?
No, that would be A2. If I want to get A1, this N would have to be -1, right? Okay, so that's one little thing. And normally N starts at 1 because N, we use that letter when we mean we want it to be an element of the natural numbers. I don't know if you guys have ever seen that symbol. Element of the natural numbers, which is 1, 2, blah, blah, blah. Actually, it doesn't have to be, but it normally is. All right. So now I can do A3. And just going right along with this. What is N in this case? If I want A3, what's N?
1.
1. All right. So now I know what to put there and there. Is everybody with me? You guys okay? Professor Hand? All right. And so now I can throw this in. 4 times 2 over 5 times 3 is 8/15. A4 is going to get kind of gross, ain't it? Poor little A4. Never did nobody wrong. So now you can see that, this is 2 and this is 1. This is 2 before, this is 1 before. Do you guys see that? So 2 before over 5, 1 before. And then you throw in what you know. I know that A2 is 3. And I know that A3 is 8/15. 4 times 3 times 15 over 5 times 8. Is everybody cool what I just did there? Divided by 15 is times 15/8, and that just makes this whole thing so magical, so much easier. So I get 9 halves, and then I can keep going till I go crazy. I like that example. I didn't know where I was going with that, but that's kind of a cool example. Now, obviously, we are barely scratching the surface of what sequences are for, why we want to define them in certain ways. When do you want a recursive definition? When is that better? When is it worse? If I have a recursive definition, can I make a straightforward definition out of it? Yes, sometimes, not always. All right, but that's a lot of other shit that we obviously don't have time for, right? But this is just the surface. Okay. Is that cool? Is that all right? I think that pretty much closes the door on section 13.1. I do want to talk a little tiny bit about the 2 sections I made extra credit, because they actually kind of rear their head in 13.4. There's something called Arithmetic Sequences. And the nice thing with this one is A for addition. They're based on addition. Something like the very first one we did, 1, 4, 7, 10, blah, 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 right? Can you take a minute and see if you can just come up with a definition to discover all of these? And while you do that, let me make sure some notation for what I'm about to say, if they use the same notation. Why do I have that dumb song in my head? I have no idea. All right. Do 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 do. All right. What notation do you people use? Okay, good. All right. This seems like it shouldn't be that difficult, right? This is a very simple sequence. Can somebody tell me like two of the main features of this sequence? What is the main feature of this sequence?
Add 3.
Add 3, that is the main feature, which is why it's arithmetic. I keep adding the same number. The other main feature of the sequence, does somebody know? It's written in purple.
A1.
Yes, it starts at 1. And what we call this is the common difference. We give this the letter D for difference. So does anyone have anything they think might be correct? I don't know. It's 1 plus something. So watch this. A1 is 1. A2 is 1 plus 1 3. A3 is 1 plus 2 3s. You guys see what I'm saying? Isn't that true? A1 is 1. A2 is 1 plus 3. A3 is 1 plus 2 3s. So it's like that's the number of steps that I have to take, and each step is 3 big. A4 is 1 plus 2. Get out of there, 2. 3 times 3. So what's AN going to be?
N minus 1.
Kick ass. So in general, for an arithmetic sequence, AN is A1 plus N minus 1 times D. All right, so that's my 2-minute lecture on arithmetic sequences. Let's do my 2-minute lecture on geometric. So that's 13 too, right? That seems like doable extra credit, right? Blah, 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 blah. So what do you think geometric sequences, the G gives nothing away, unfortunately, but what do you think they're going to be based on? Arithmetic was addition. Geometric, there it is. Geometric is probably what?
Subtraction?
No, because subtraction is addition. So if I have a, real quick, I'm sorry. If I have a, since you said that, if I have an arithmetic sequence, I could just make D negative, and then it's like subtraction, right? So addition, subtraction are the same thing. There is no subtraction. There's just adding the opposite. So geometric is going to be based on, I'm sorry?
Multiplication.
Multiplication, crazy. So for example, what you got, Jeff? 2, 6, 18, 54, blah, blah, blah. Right, so A1 is 2, A2 is 2 times 3, A3 is 2 times 3 times 3, so that's to the first power, so that's to the 0th power. Holy shit. 2 times no 3s, 2 times 1 3, 2 times 2 3s for the third one. So what's AN going to be? 2 times
3 to the n minus 1 power.
You guess. I love it. And the stupid n minus 1 is because we don't let this be a0. You get a little further in math and you start letting this be a0, and then this will be cleaner. This would be 2 times 3 to the n, which is cleaner, but oh well, too bad for us. How you guys doing with that? Is that all right? So in general, an is a1 times r to the n minus 1. That's geometric. Geometric. Boogie, boogie, boogie. All right. Pretty nice, right? Pretty nice. That's why I made him extra credit, just to, so I didn't have to spend more than 2 minutes. Nobody could yell at me if they were like, you didn't lecture long enough. Well, then don't do it. All right. So that's that. Now here's where we get into more interesting stuff. Series. All a series is if I take, let's do this one. Well, let's do this. Nah, screw it. We'll do this. If I take a sequence and I add their elements, not necessarily forever, but it could be forever. If I did this one forever, what would the answer be? You know,
Infinity.
answer. Yes, infinity. I like it. We would say that it does not converge, is the technical way to say I have an infinite sum. It just doesn't converge to something. Can you imagine a case where I'd have an infinite sum that does not go to infinity? I'll tell you it exists. A lot of them exist. They're all over the place. Here's one. You ready? It's my favorite one. Bam, bam, bam. That's an infinite number of numbers, correct? With my little ellipses at the end, but right. What is that approach? Does anyone know what that sum approaches? Who?
0.
No. It's definitely not 0 because that's 0.1 and then it's increasing from 0.1. I mean, one answer you can give me is this, right? Isn't it that? Don't I get this at the end? Are you guys understanding? Wouldn't this be 0.1111111111? Do you guys see that? Let me ask you this way. Anybody not see that? So I want you to notice something. This goes to infinity because these guys don't get out of this one's way. That doesn't make any sense right now. These get out of the way of the first one. I don't know if you guys see what I'm saying. So they go over to the next decimal place. So they don't over, and then the next guy goes to the next decimal place. That's the most basic way to create a sequence that ends up converging to a finite number. Does anyone know what that looks like as a fraction? You actually do. What's 0.333333 forever? You guys know. What's that as a fraction? I know somebody knows. 0.333333 is what fraction? Say again.
3/9.
Sorry? I can't quite hear you. What? Say it again.
1/3.
Third.
1/3. I love it. Isn't 1/3 3/9? Right? Come on, guys. If I divide both sides by 3, don't I get that? 0.33333 is 3/9. 0.22222 is 2/9. 0.11111 is 1/9. Isn't that beautiful? That's so beautiful. All right. I don't know if you guys are reacting at all. You're all like, all right, more numbers. More numbers. Put them up there, Jeff. More stupid numbers. Okay. So there is a, I wanted to keep that up here because that's a little more interesting. But let me see. How would I represent this? So let me before we get into the specifics, we'll come back to this one in a minute. in general, if I have A1 plus A2 plus A3 up to AK, I would represent that using this symbol. Does anyone know what the Greek letter, what this is the Greek letter of? What letter of ours is this related to? That's a sentence. What letter of ours is this related to? Do you guys know? It's not the letter E, just to kind of stop you there. Does anyone know this Greek letter?
That's gamma, right?
No?
Never mind.
I appreciate the attempt. This one's called sigma. So it's the Greek letter S. And the reason we use it here is because we get, it's a sum. So let's use S. And we made it Greek to make it look more official. So this is the sum. So this by itself actually means nothing. It's sort of like me talking about this symbol, but it doesn't mean anything unless something's inside of it. So the sum of what? Well, this would be the sum of this. Right? That would be the sum of A sub n. But what's it go from to? From the what term to the what term?
A1 to AK.
So the first term to the kth term. I like it. So for example, here, before we do this kind of thing, let's do it the other way. If I have this, what you got, Jeff? It doesn't matter, dude. It doesn't really matter. There you go, buddy. So you got kind of two layers to this. You got to figure out the terms of the sequence, but as you do that, you just put plus signs between them. So now be careful, what n am I starting at? What's the first element?
2.
2. So what do I get here? Yeah, I'm sorry. So your answer is kind of funny. You start with 2 and the answer here is 2, right? So this will be 2 squared minus 2 plus, and then you go from 2 to 5. Jeff, you could do it. There you go, buddy. 4 squared minus 4 plus 5 squared minus 5. So these are the sequence elements. So all a series is it's taking a sequence and adding components up. And you can define which ones you specifically want here. So notice you don't have to start at 1. You don't have to go to infinity, thankfully. And then whatever the shit that is. I don't know. What is that? 8, 20, 40. Is that right? Is that 40? By the way, this is not a symbol of a function. Don't worry. I'm just going to go with it. And somebody tells me it's not right. I don't know. I'm not going to redo it. Okay. So this guy, let me show you this. So if I do, now real quick, coming back to this guy. Let me write him in a better way. What is that as a fraction?
1/10.
1/10 plus 1 over 100 plus 1 over 1,000. So can you write what the sequence looks like if I start at 1? What would that sequence look like? Anybody?
Would it be 1 over n over a to the power of n? No.
So, but power of n I like, but it'd be 10, right? So when n is 1, you get 1/10. When n is 2, you get 1 over 10 squared, 1 over 100. Is that cool? And what does this mean? I want to go how far? I want to go
To infinity.
Forever. Yeah. But not beyond. That would be calculus. Maybe you can get beyond. You go to infinity plus 1. Okay. We actually know what that is. We just figured that out a minute ago. It's 1/9. Isn't that weird? Anyway, all right. That's just a side note. Don't worry. You're not going to have to figure out what these are. That was one example I could show you exactly what it comes out to be. But there's no way in hell, even if you understood what all these mean, if I didn't go through everything I did earlier, you would have no idea what the shit that would equal. Right? Unless you wrote it out and looked at it for a little bit, you could figure it out. The important thing now is to get used to what this means. This means these create specific elements, and this guy tells me to add each element that these make. So that's what a series is. A series builds on the idea of a sequence. It adds in adding. Sorry. Couldn't stop that from happening. All right, now watch this. This is where things get really nifty. I don't think this has come up yet for us. Let's go back. Look here, for example. What kind of sequence? Let me see if you guys remember what we just talked about. What kind of sequence is this? Specifically, it's got a very specific name. Not very specific, but it's a certain type. How do I build that sequence? What do I keep doing?
Adding 1.
Adding 1. So what kind of sequence is this?
Arithmetic sequence.
Yes, arithmetic. So this is an arithmetic. So we like to pronounce it arithmetic when we're talking about sequences. Otherwise, you can call it arithmetic. So this is an arithmetic sequence. Sounds like it needs pills for that, but it's going to be okay. Can somebody tell me? So obviously, what's so A1 is 1. Jeff, what are you doing? And it goes up to 100. So the last term is 100, and D is 1. Now here's the thing. All right, stay with me, guys. There's actually an urban legend in math that says, unfortunately, it's not as interesting as other urban legends. You can't really make a movie out of this and make any money. I don't know if the urban legend movies made any money, but anyway, there's an urban legend that Gauss, this young man, anybody ever heard of Gauss? Have we talked about Gauss before? Probably not. Yes, we have? Oh, yeah, we saw his picture, didn't we? Yeah, we did. Okay, cool. Gauss, I don't know if I said this at the time, he needed to slow the shit down. My God, other math people like, hey, can you leave some shit for us to do? Please stop discovering things, Gauss. So there's an urban legend about when Gauss was in grade school. And the teacher was like, the students were going crazy. So the teacher said, everybody, sit down. And I don't know. So add up all the numbers from 1 to 100. Add them all up. And don't say a word till you're done. And then he sat down and started reading his book. Gauss, supposedly about 10 seconds later, comes up. Here's the answer. Sir, I'm going to go cause a ruckus now. Thank you very much. And so the professor sat down and said, holy shit, okay, what is 1 plus 2 is 3 plus 3 is 6. And he finally got to the end and saw that he was right. How the shit did Gauss do it in 10 seconds? One theory is a time traveler came back and gave him a calculator, but that's not true. Didn't happen. I don't know if anybody knows the shortcut for this type of sequence. It works for every arithmetic sequence. Somebody tell me, what is 1 plus 100?
101.
101. What is 2 plus 99?
101.
101. What is 99? Well, right. So what's the repeated sum? It's A1 plus AN, the last one, and that's 101. And how many 101s will I get? Basically, how many pairs can we make?
50.
50, n divided by 2. 50. So look at this shit. This is a cool fact to know. the first 100 natural numbers add up to be 50-50. You got to love that shit. You have to love that shit. You just have to. Isn't that neat? Come on. 50-50. No? Okay, whatever. What else can I do? So it works. This works for every arithmetic sequence. If you stop, right? What's the sum if you go up to and stop somewhere? Now, obviously, if you go forever, it only works if it's a certain kind of arithmetic sequence. Yeah, anyway, those are not very interesting. All right, so let's try another one. Let's see, what do you want, Jeff? Let's do one like, nah, screw that. Let's not make it too freaky, Jeff. Yeah, this one looks nice. You could do it, buddy. I can't add. Are you kidding me? I think I did that right. Okay. So obviously, I'm at least trying to make this go up by 7. I think I managed it, did I? Yes. So to do this, what's n? 1, 2, 3, 4, 5, 6, 7, 8. This works. Let me do this. This works even if I have an odd number of things. Right? Don't want you to think I'm cheating. So n is 9 now, right? So this will be, how do I figure out the sum of the first 9 things? So the sum of the first, yeah, sure, 9 things is going to be n divided by 2 times 5, the first guy, plus the last guy. Do you guys notice what happens? This will always happen. If that's not even, that will be. I mean, if I'm talking about, as long as I don't have fractions or decimals in my sequence itself, if that's not even, that will be. So this is 9 times 66 divided by 2 is 33. And that's 297, I think. Possibly. And then if you check it, if you actually add this shit up, it will come out to be 297. That's a semi-decent, nifty little sort of thing, right? Kind of almost. All right. All right, let me think. What else do I want to do with this? I think that's it for this. Yeah, okay, I like it. Yeah, maybe I'll do that with you guys. Yeah, let's try that out. Let's look at geometric sums real quick. Oh, shit. Hopefully you guys all got that. So geometric series, meaning the sum of something in this form, right? Don't worry about the n-1 bullshit. Don't worry about it. To something. All right. So there is a notation for what's called a partial sum. And it's kind of nice. It's kind of nice. Like if I want, a better way to write this stuff is to say I want the nth sum, which just means take this and go up to the nth term. So it's kind of nice. A sub n is elements of a sequence. S sub n is the sum of those elements up to that element, right? So A7 would be the 7th element. S7 would be the sum of the first 7 elements. So this is cumulative up to that. So this would be A1 plus A1 times R. I guess I am going to bring in the, it doesn't matter, the minus 1, plus A2 times R not A2, plus A1 times R squared plus A1 times R cubed up to A1 times R to the n, right? You guys with me? Stay with me. This is really neat. This is a little bit freaky, but it's really neat as shit. So the idea of a partial sum is general. It works for every series. It can have a partial sum notation, but this is specifically for a geometric series I'm looking at. Now watch this. This is kind of cool. This is a neat little weird thing. If I multiply this by R, what happens over here? This just becomes A1 times R, right? So let me I'm going to move that over. Is that cool? Do you guys see what I'm going to do? That becomes A1 times R. That becomes A1 times R squared. Up to, that becomes A1 times R to the n plus 1. Let me stop for a minute. All right, guys? All I did was multiply everything by R, which means everybody's exponent gets one bigger than it was. One bigger than it was. All right, this is really, really freaky. And to be honest, I'm so happy I remembered how this works because I did not look at this shit beforehand. I didn't think I'd be doing this, but I figured, why not? Now watch what I'm going to do. What if I take Sn and I subtract R times Sn? Now, you know, some of you guys might have known I was going to do that shit. This cancels. This cancels. You cancel. You get a car. You cancel. Right? That is okay. That dies. So what do I get? I get A1, die, minus A1 times R to the n plus 1. Stay with me. There's a point to this. You're all like, where's this guy going with this? Oh, it's so close. The end is so close, Jeff. The semester is almost done. All right, now watch. I'm going to keep going because I'm insane. Sn times 1 minus R. Is that cool? A little factoring. Ooh, a little factoring. And then I can factor this shit. And then I can divide by 1 minus R. Something tells me I did this a little bit wrong, but oh well. I think, what would I have done wrong, Jeff? I don't know. It feels off, but I guess I'll be all right. We're going to check it here in a minute. So now I know, now look what this tells me. I know the partial sum for a geometric sequence. All I have to know to figure it out is the first guy, what R is, and I can figure out what the sum is. That feels wrong. Let's check it. Something feels wrong about that. So let's do this with a nice 2, 6, 18, 54. Sure, we'll go like that. Just go with me. We're going to do a very simple example to see if that works. So this is obviously A1, A2, A3, A4. So I'm going to want S. Jeff, are you kidding me? All right. So let's check this out. If I just add these up, I get 8, 26, 80, right? So I get S4 is 80. I can see that. So let's see if this gives me that same thing. S4 equals 2. This is what I'm worried about. I don't think that's quite right, but let's find out. What is R, by the way, in this problem? Do you guys remember? Oh, I don't. Yes, I did. What is R here? R is just what I keep multiplying by. So what is R?
3.
3. I love it. So 1 minus 3 to the n plus 1 divided by 1 minus 3. Oh, good. No, see, that is wrong. What did I do wrong? Oh, well. I tried to do it on the fly. Something went a little freaky with my exponents. What did I do? I don't know. So that is supposed to be an n there. That's what I was questioning myself about. Not sure what I did wrong. I don't know if you guys can see why I can see that that's true. 3 to the 5th power is 243, which is bad. but 3 to the 4th power is 81, right? I don't know if you guys are with me or not. 3 to the 4th power is 81. 1 minus 81 is negative 80. 2 divided by negative 2 is negative 1, so you would get 80, which is what this is. All right, so this is a good, if anyone wants to be a teacher, probably before you do some weird ass shit like that, you should probably sketch it out real quick. So somewhere I lost track of my exponents. So that's supposed to be an n there. That's my bad. So now if you go through this, 2 divided by negative 2 is negative 1. 1 minus 81 is 80 negative. So you do get 80, the same thing. I'm upset at myself. What did I do? What did I do? Oh, I know what I did. Gosh, that's, yeah, okay. Now I know what I did. All right. You silly boy. Anyway, I'm not going to redo it. All right, so that's kind of interesting. So these little things are going to come up in the work in section 13.4, but they're just little formulas to plug stuff into. This means the first term. This means what number you keep multiplying by. Okay. Now, let me ask you this last question here. That this problem here that actually converges, what kind of sequence is this? To go from this one to this one to this one, what am I doing? How do I go from 0.1 to 0.01? What do I do to 0.1 to make it become 0.01? To then make that become 0.001? Do I keep doing the same thing? Anybody? Anybody?
You divide by 10.
Yes, so I multiply by 1/10. I love it. Right? Division is multiplication. So this is a geometric sequence. But this is a type of geometric series, my bad, series because of the pluses. This is a type of geometric series that I can actually add even if it goes to infinity. And that's the one. All right, Jeff, it's been too long. I'm pretty sure I know what it is, but I don't want to. Oh, do they even have it in here? Maybe not. Do I want to go that crazy with you guys? Oh, there, that's why. This is kind of nifty. All right, they got that in there, good. They got that in there, good. And do they have this last piece in here? No. Oh, but do they tell you what it is? Ah! There it is. Okay, so it is what I thought. Okay. So what's special about this sequence is that R is less than 1. If the number I'm multiplying by is less than 1, I can figure out the infinite sum. So S with no subscript is just the complete total sum. It doesn't stop anywhere. So this is funkydelic right here. So watch this, watch this. So that is the formula. And I'm not going to make you memorize these formulas, by the way. Right? It's just too jam-packed at the end of the semester. Don't freak out. I didn't even remember this one myself, so I'm not going to make you memorize this. I should have known that, but too bad for Jeff. I haven't looked at it in a long time. So watch this. The infinite sum. We already know the answer to this for the infinite sum is 1/9, right? We did that earlier. But if I do this, A1 is 0.1 and R is 0.1. Is that right, Jeff? Yes, you keep multiplying by 1/10. So wouldn't this be 0.1 divided by 0.9, which is 1/9? Is that, do you guys see? That's kind of neat. So we showed this one way earlier, but now when I get uglier sequences, but r is less than 1, I can actually do the infinite sum. All right, maybe. So there's kind of a decent amount of stuff in there, but the math involved is not very complicated, right? I'm not going to make you memorize these formulas, okay? I really just want you to get used to summation notation, this guy. Because this is the guy that shows up in all kinds of levels of mathematics. Has anyone ever taken statistics before? If you have, then you should know this symbol, right? This symbol is in a ton of statistics formulas. This is all over the damn place, yeah. Okay. All right, wow. I'd say that's pretty good. For tonight, I thought maybe if there was time, we'd look at the practice fund. We can save that for starting tomorrow. So what the plan is, Thursday is the first night of practice of final exam review, and then Monday is the second night. So come with questions ready. If nobody has any questions, we're just going to start going through the practice final. Why not? One thing I did for my stats people, I don't know if I'm going to do it for you guys, is I have kind of like a complete listing of all the ideas in each chapter. That's what I would do for myself when I was a student, is I would write all the ideas in each chapter. And there's just kind of like circle the ones that I really didn't feel comfortable with. And then I knew where to kind of start. I mean, I was such a geek. You would say something like partial fractions, and I would tell you what section it was in, right? So I'm not saying you have to go to that level. That's just me. But yeah, okay. So just come ready tomorrow with any questions from the entire freaking semester. And that's why I wanted 2 days worth of final exam review. Otherwise we're done. So if you don't have any questions for tonight, you can head out.
I
If you
just
do, let me
wanted
know.
to
Yeah.
double check that chapters 1 and 2, because they were a review, those ones aren't going to be on the final. So technically it starts as chapter 3, correct?
Sort of. Yeah. I mean, they won't explicitly be on the final.
Mm-hmm.
All the ideas in there we've used throughout the semester. So I'm not going to have explicit, probably not. I think on the practice final I do, don't I? Don't I have some like really basic shit on the practice final? Yeah. But you know, there's enough stuff that I'm going to have to throw a decent amount of stuff out just to have a normal sized final. So what exactly will I throw out? We'll all find out on the day of the final.
Okay, thank you.
You're welcome. Teachers are kings of the unsatisfactory answers. All right, guys. I'll see y'all tomorrow.